So, I have thought, let me close the lectures on material and heat balance by giving a lecture on thoughts on energy balance. In the lectures on material and heat balance, we have done enough about fuel saving and carbon credit. Both concepts I have illustrated by solving the problems. Now, what can be done beyond fuel saving and carbon credit? I have given a thought over it, and let us think what in fact we can do beyond fuel saving and carbon credit calculations. We have recognized that fossil fuel energy availability, is associated A, discharge of CO2 in the environment along with other harmful impurities. It is also associated with unutilized thermal energy carried by A, or rather carried by one, say product. So far we have not paid any attention to the product, and B, by products of combustion. In the product, there are several types of products are being produced. For example, you heat the steel, so steel discharges at 1200 degrees Celsius. So, the product that could be, depending on the objective, it could be steel, it could be slag, it could be coke oven gas, because your objective is to produce a coke. I mean, it is the coke and like other. So far we have not addressed what can be done by the heat which is carried by the product. Now, for example, say 1 kg mole carbon on combustion, it gives 1 kg mole CO2. 1 kg mole CO2. So, therefore, say 12 kg carbon will discharge 44 kg of carbon dioxide. This is one particular thing, and also we have said that large amount of heat will also be carried away by the product and products of combustion, and that heat we call sensible heat. So, sensible heat, you know, I am not talking at the moment the calorific value, I am talking of the sensible heat. So, sensible heat, that is M Cp T of product or byproduct minus 298 if 298 Kelvin is taken as a basis of calculation. Depending on the temperature of the product, a large amount of sensible heat will also be carried away. We have already addressed what can be done by the sensible heat of the byproducts. We have tried to recover, recycled into the furnace, and did lot of calculation. Now, the sensible heat is also very important. Say in sensible heat, for example, in byproduct, for example, the gases are there. So, the gases are discharged also at 1100 or 1200 degrees Celsius depending on the temperature of the furnace. Unless the gases are cleaned, they cannot be used directly. But then what happens to the sensible heat of the product? Now, let us consider and concentrate now, let us concentrate on sensible heat of products. sensible heat of products. So, the example for example 1, say for thermomechanical processing, steel is heated to 1200 degrees Celsius, heated to 1200 degrees Celsius approximately, and its heat which is available with the steel is then utilized for thermal mechanical processing, that is for direct rolling. You must have also seen in coke making, coke is discharged at around let us say 1200 degrees Celsius. It is very difficult to store the coke at this particular temperature. So, for this purpose coke is water quenched and brought to the temperature of 25 for storing purposes. In an attempt to water quench coke, large amount of water is used. Water contains large amount of contaminants, a large emissions due to wet quenching of coke is discharged into the environment. What I have thought, let us consider a coke making and what can be done with the sensible heat of coke. So, I will concentrate now my lecture on the sensible heat in coke. Now, first of all, as we already seen in the lecture on coke making, for example, on lecture 27, that coke is not a naturally occurring fuel, not a naturally occurring fuel. Number 2, coal is carbonized. The details you can find in the lecture 27. Also, coke is an important source of thermal and chemical energy in integrated steel plants Now, just to give you a figure, say 1 ton of hot metal, hot metal means the pig iron, it requires 500 kg of coke. Approximately the figure may vary, but just I am taking an example. 1 ton of hot metal, produces approximately 0.75 tons of steel. Now, 1 ton of bituminous coal, on carbonization say produces 700 kg of coke. That means, now if I combine all together, then I can say that 1 ton of steel, would require 940 kg of coal. If I take now 10,000 tons of steel, that would require 9,400 tons of coal, and approximately 6,600 tons of coke. What does it mean? You are not producing 10,000 tons, annually you are producing million tons of steel. A huge amount of coke is required in almost all integrated steel plant. So, that means the conversion of coal to coke and the sensible heat which is available in coke is a very important thing to consider what can be done. So, what I have thought now, let me give you a heat balance of a typical byproduct coke oven. So, let us consider now say heat balance of a byproduct coke oven. Now, here I have selected the heat balance vis-a-vis material balance. First we have to do it in the lecture 27, which is material balance in coke making. One of the examples which I have presented over there, I have used the data of material balance to illustrate the energy balance or heat balance over here. So, I am just now putting say in a form of a diagram. So, here I am presenting the heat balance. So, here what we are doing, I am putting now 1000 kg coal whose calorific value is 8184 kilocalorie per kg. CV so far you must know it stands for calorific value. So, on discharge we get coke, its amount is 724 kg, its calorific value is 7481 kilocalorie per kg, its Cp that is equal to 0.359 kilocalorie per kg into degree Celsius, and it is discharged at temperature 1200 degrees Celsius. That is what we are considering. Another product as we have shown there is a tar, which amount is 40 kg and its calorific value is 8776 kilocalorie per kg. It is also discharged at 1200 degrees Celsius. Then another product is say coke oven gas. Coke oven gas whose amount was 349 meter cube, calorific value 103 into 10 to the power 3 kilocalorie per kg mole, and its density is 0.44 kilogram per meter cube. Now, what I am doing now, let us now this coke oven gas, say 40% of coke oven gas, 40% of coke oven gas is burnt and it is used to reheat the walls of the byproduct coke oven. You know that there is an indirect heating. So, given all these figure, now we can do the heat balance and let us see what the heat balance brings. So, I will use the next page. So, let us do now the heat balance. Typically, say heat input in kilocalorie, say CV of coal, then we have CV of coke oven gas because we are combusting it. So, CV of coal is 81484 into 10 to the power 3 and that is here is 704 and 10 to the power 3. Now, let us go on the heat output. Heat output again in kilocalorie, then CV of coke we have 1, then CV of tar we have another, then CV of coke oven gas, then important sensible heat in coke, sensible heat in coke and sensible heat in coke oven gas. Now, let me just to concentrate on this one sensible heat and sensible heat. Now, these values are over here, that is 5416 into 10 to the power 3, here 351 into 10 to the power 3, here it is 1053 into 10 to the power 3, sensible heat in coke 305 into 10 to the power 3 and sensible heat in coke oven gas 174 into 10 to the power 3. Now, this is what a heat balance picture is before us. For example, calorific value of the coke, well, that is not lost even in the water quenching. On combustion, this energy will be available, no problem. CV of tar, it is also available because it is the potential energy, it is also available. Similarly, calorific value of coke oven gas is also available because it relates to the potential energy. On combustion, you will be getting. What about sensible heat in coke oven gas? You know, the coke oven gas contain large amount of entrained particles. So, you have no option except to cool the gas and clean the gas, and you can use only its potential energy. Unless the gas is very clean, the sensible heat of the coke oven gas is not possible to use. For that matter, any gas which is coming out, if it is containing entrained solid particles, it is very difficult to use because it will contaminate all the appliances which you use for recover the heat. Now, in this particular case, what happens to sensible heat in coke? Sensible heat in coke, you cannot use it because it has to be wet quenched in order to store it. You cannot store coke at around 1200 degrees Celsius. So, that means what? We can see from here that sensible heat in coke, which is very large in amount, at present it is 305 into 10 to the power kilocalorie per 724 kg of coke, which is equivalent to 436 into 10 to the power 3 kilocalorie per ton of coke. What happens? On wet quenching, this energy is lost. So, what you are doing on wet quenching, one thing that you are doing, that is you are losing the sensible heat, that is okay, but the second thing that you are doing, you are harming the environment. You are using a very large amount of water, say approximately 0.5 to 0.6 meter cube of water is required per ton of coke for wet quenching. Now, the water is sprayed on hot surface of coke, which is at 1200 degrees Celsius, the water is vaporized along with the contaminants, because water nearby the integrated steel plant is not pure, it has lot of contamination. So, all those contaminations are evaporated into the atmosphere. So, large amount of emissions are discharged into the environment. So, that means along with this airborne coke dust, that is also discharged in the environment. Now, considering the amount that you are converting per day, or the coal which is carbonized per day, In a plant it could be 10,000 tons or whatever. You can imagine the amount of heat which is being lost by wet quenching and the emissions which are being produced in the environment. Do not you think that this particular heat balance which you have done, it provocates you to think, can we do something on the sensible heat of coke? Is it not possible to do something on sensible heat of coke which is largely going to waste, not only waste, but it is also polluting the environment? Do not you think that this heat balance exercise that you have done for the coke byproduct coke oven plant, does it not help you to innovate or to think along the lines that can we do something to use the sensible heat of coke? And it is this particular thought that I want to tell you, that if you do the energy balance and if you try to analyze, as we have done analysis of each of the output heat, if you do that analysis, then you will come across innovative ideas which is a need of the hour, because everywhere we are talking on the energy security and environment sustainability. If you do this, you will come with an idea, and in fact that idea is working in the plant. Why not to evolve a mechanism of quenching of coke not by water but by gas, and this mechanism is called dry quenching technology. So, that is what my objective of this particular lecture is, to provocate you to think, after doing the heat balance, to think in terms of, can we save energy? Number one. Number two, can we contribute to the environment sustainability or not? And that is quite possible. You are seeing now also here the magnitude of the heat that is also available, that is an important. So, this is a thought process which has given the so called dry quenching technology, and dry quenching technology, it can also be considered under the Kyoto Protocol as a technology which contributes to clean development mechanism. In short, it is called CDM. There are several clean development technologies, sintering, pelletizing. This is one that I will illustrate what can be done by performing heat balance of a high temperature process. So, dry quenching technology, you can call it as a technology which contributes to clean development mechanism, which means that this technology reduces the emissions in the environment. So, in fact, the advantages of this dry quenching technology, first of all, it eliminates emission, of course, because now you are dry quenching, say maybe you are using air, maybe you have air, you cannot use it because that will react with the coke, you are using a inert gas, could be argon, could be nitrogen, whatever. So, it eliminates emission. And second important thing that you are doing by dry quenching is that now you can capture the sensible heat and you can reuse it. That means, you can invoke the basic concept of energy security and environment sustainability is capture and reuse. So, the second thing that you are doing, you are capturing the heat, and reusing it, that is called cogeneration. Well, this is what an idea which has emerged. This can be done, these are the benefits. Now comes the question of development of technology. Because when you talk of the technology, it is related with the finances. That technology should be workable. and so on. Now, well, this is well established technology, but what I am telling is those ideas, if it is to be translated on the technological thing, then several other things are required. Now, this technology should have at least two components. One component is say capture of sensible heat, capture of sensible heat is one component. Now, this can be done in which the gas is flowing counter current to the flow of coke. That is, you have to design a reactor where coke may be flowing from top and discharge from the bottom, and the gas is flowing from the bottom in a reactor and discharge from the top, because a counter current mode of heat exchange is a very, very efficient method of heat transfer. So, the one component it should have a capture of sensible heat. However, you have to have a mechanism to charge the coke, to have an inlet for gas and so on. They are the part of the technological development, but important component is the capture of sensible heat. Of course, here a counter current mode is very effective. A counter current mode is effective, because then you have to synchronize with the flow or with the amount of coke that is dropping and amount of gas, and this synchronization is a part of the development of the technology. Another component is, well, what you have done with this? You have passed the gas as 25 degrees Celsius and coke, for example, at 1200 degrees Celsius. You allowed enough residence time, so that the gas is heated, for example, 400 or 500 degrees Celsius or 600 degrees Celsius. What will you do with that gas? Now, you have a gas which is superheated. I mean, I do not use the term superheated, but it is heated to 600, depending on the residence time and height of the reactor, it may go even higher temperature. 600, 700 degrees Celsius, you have heated the gas. What are you going to do with that gas? So, the second component is use the heat which is available to you in the gas to produce, for example, superheated steam. Superheated steam. Or there could be other uses also. You want to heat some appliance or something which I do not know, anything could be, because now you have the heat which is available to you in the flowing gas, and it has to be used. One of the important use is to produce a superheated steam. Now, superheated steam means, because you have a temperature of 600 degrees Celsius of the gas, water evaporates at 100 degrees Celsius. If it comes into contact, water may be, and the evaporated water may be at 300, 400 degrees Celsius. So, it is a superheated steam, large amount of pressure will be generated. So, superheated steam. Now, for example, in a boiler, superheated steam in a boiler, now you have to think what you are going to do with that superheated steam. So, a large amount of steam you have stored, what you are going to do? You can do nothing. So, that idea should also be there. For example, this superheated steam can be used, for example, to run a turbine. So, what I mean to say, that these are the things, or these are the technological challenges which have emerged out of heat balance, and after giving a sincere thought that what can be done with the available heat. Now, I will just give you a flow diagram of a technology which works on the dry quenching. So, here what you have, say you have a reactor, for example, this is the reactor. So, here you have the so called coke ejector. This is the coke ejector, and here you have a hopper. Here the coke at, for example, 1050 to 1100 degrees Celsius is charged. So, the coke, it moves downward as the heated coke, downward and cooled, and coke is discharged through the bottom. Now, say the hot gases from here, this is the gas, they are collected here, and the hot gases, they are taken in a boiler. So, this is the line for hot gas, and here somewhere you have a primary dust catcher. So, this line enters into a boiler. This is sort of boiler. So, this is the gas, it passes here at the temperature 800 to 900 degrees Celsius, and this is the primary dust catcher. You know, it is important to remove the dust. This is the primary dust catcher. What I mean, these are the component of the technologies. You have a reactor, you have the gas flowing pipeline, you have the primary dust catcher which rather removes the dust. Then you have to pass through the boiler, so that water gets heated up. Now, the gas which is cooled, say it may be it may not have 800 temperature, it may be around 170 to 200 degrees Celsius. You have to think what you are going to do with that gas. So, now say another, say dust catcher, this is a so called secondary dust catcher. Secondary dust catcher, you know, you require, because you have to be sure that the particles which are there, it may not contaminate the boiler and so on. So, you require all these small things, but then you must think, and then you might be require a pump to boost the pressure, so that the gas can flow. So, this may be a pump over here. So, this is a sort of a gas circulating fan. Gas circulating fan. Now, from here it goes to a preheater. Let me draw it. This is the one. This is the, I mean, just a preheater, and from the preheater the gas again enters over here. So, here again the gas, and this is the so called preheater. And the coke ejector, now the coke, it comes out at around 200 degrees Celsius. So, you see, by developing this particular technology, which is called the dry quenching technology, you have contributed not only to recover the sensible heat, but also you have created an environment where steam can be produced and turbine can also be run. So, this is a typical example of this. So, let me now illustrate another example of fuel saving, though I have illustrated in my earlier lecture, but I thought let me do once again here. So, I will take different problem, say on second case. Now, consider heat balance, of a continuous reheat furnace, I will not be going into detail of all calculations, you can do yourself what I am representing. So, let us take it now. This is a reheat furnace, which is used to heat steel to, for example, 1400 degree Kelvin, typically for rolling operation. Now, this furnace is, let us say, oil fired. This furnace is oil fired, and consumption of oil is 100 kg per hour. Its net calorific value is 40,000 kilojoule per kg. Rate of heating of billet, say it is 13 tons per hour, it is a huge furnace, and the composition of oil, let us say carbon 85%, hydrogen 14% and sulfur is 1%. Now, I have calculated the heat output in terms of heat output. For example, steel and calculate the heat output that I have done, that is 5.63 into 10 to the power 5 kilojoule per hour. You can calculate from mCp delta T, m is already given to you, which is 13 tons per hour, and temperature is the steel I considered here, the discharge temperature of steel is 1500 Kelvin. So, that can be done because we have done at several places. Then 2.4 into 10 to the power 6 kilojoule per hour is heat to POC, heat to POC. Now, this much amount of heat is heat to, which is taken away by the steel. Then 1 into 10 to the power 6 kilojoule per hour is the amount of heat losses. Now, some data I am giving here, what I have taken Cp of POC, I have taken average Cp of POC, that is 1.05 kilojoule per kg Kelvin. Amount of POC you can calculate, amount of POC, that is 19.25 kg per kg oil. Then amount of air, that is equal to 25% excess, then theoretical. So, given this data you can do this calculation. My objective here is to show you by calculation in this particular scenario where we are not using any heat, then the fuel consumption is 100 kg per hour. Now, again if we see this heat balance in the form, you note that the heat which is taken away by the steel, nothing you can be done it. Only the steel is directly taken to the rolling mill. So, you do not require to again give the heat for rolling purposes, that is one. Heat losses, well, you also cannot do it because it is limited by the several parameters, water cooling, opening of the door, through the walls and so on, these also cannot be done. Now, if you think in terms of bringing down the fuel consumption of 100 kg per hour to a lower value, the only alternative that seems to be applicable in this particular scenario is what can be done with the heat to POC. What I mean, if you are working in a plant or in a rolling mill where rolling is done, steel is heated to that temperature and they are not using that particular heat, heat balance is before you. So, you should think that what can be done to bring down the fuel consumption in the existing furnace. Mind you, I am talking of existing furnace, and here by this heat balance you come to the knowledge, or it comes to your knowledge that well, it is 2.4 into 10 to the power 6 kilojoule per hour of heat is being taken by the POC. So, naturally this heat balance gives you an idea that why not to capture and reuse the heat simultaneously. So, the concept of simultaneous use of capture and reuse, simultaneous capture and reuse concept of unutilized heat, it can be only done by installing a heat exchanger. So, what my idea of going to this presentation or going to is very simple, is to provocate you that after doing a heat balance you should exercise your mind to think what can be done. So, simultaneously capture and reuse it can be done through the heat exchanger. So, now I will show that by heat exchanger how much amount of fuel can be saved. So, that means without noting what I am doing, this is my furnace, and to this furnace I am attaching a heat exchanger. So, this is a heat exchanger. This is a furnace. Same amount of POC that we have calculated earlier. Here say I am putting air over here at 25 degrees Celsius and a say preheated air, is now passing into the furnace. Rest all parameters are same, heat to steel is same, heat losses are same, only air is being preheated by the heat recovered from the heat exchanger and transferred to air. So, here some assumption, although we can calculate also, but I am making this assumption that 50% of heat, 50% heat in POC is recovered and transferred to air That is what we are doing it. That means, our heat exchanger is working to a capacity, so that it can recover 50% of heat and transfer all 50% of heat to the incoming air. Naturally, now since additional heat is being supplied to the furnace, we are not changing the rate of heating of steel, that is we are still keeping 13 tons per hour as constant. Now, since we are supplying additional amount of heat, we are not allowed to increase the temperature of steel. So, the only alternative is to reduce the fuel consumption. There is no other way, otherwise the temperature of steel will increase because you are supplying additional amount of heat. So, let us consider now, F kg per hour is our revised fuel consumption, Well, now we can do heat balance. Let us see what heat balance gives us. We can do heat balance, and for the heat balance, say we take one heat input, and heat input is say oil combustion, that will be in kilojoule per hour. Now, F kg per hour, so it will be 40,000, which is the caloric value into F. Sensible heat in air, we are recovering 50%, so it will be 0.5. Our products of combustion, that will be F into 19.25, that is our kg per kg, into 1.05 is its heat capacity, into it is discharged at 1500 Kelvin. So, 1500 minus 298 into 1202, that is what our sensible heat in air. Now, let us see heat output. As I have said, the rolling mill has to work what it was working earlier. So, heat to steel, it will remain same. Heat to steel, that is 0.563 into 10 to the power 6 kilojoule per hour, it will remain the same. Heat losses will also be remain same, as it was our earlier example 1 into 10 to the power 6. What about heat to POC? Heat to POC, that will change, because now our fuel consumption is F per kg. 19.25 kg per kg of fuel is the amount of POC into its specific heat is 1.05 into 1202. So, that is the heat to POC. That is what now the heat balance before us. Now, what can you do now? Heat input, if you do the heat output, then you can calculate the unknown value of F. This exercise I will leaving on you. So, if you do that, we calculate F, that is the revised fuel consumption. Now, it comes to 56 kg per hour. It comes to 56 kg per hour. That means, the fuel saving at least on the calculation front, that is equal to 44 kg per hour. Now, you can extend, if the furnace operates say 15 hours per day per month, how much you can save. So, what I wanted to illustrate through this example is that just think beyond after performing the heat balance. It is that particular exercise will give you many innovative technologies. And one particular example, I mean two examples I have given, one in case of coke making and another in case of say reheating furnace. So, these are the important things that I thought I will illustrate. Now, here itself to complete the problem, you can now perform revised heat balance, no problem. You can make it now revised heat balance. You can do it now revised heat balance and heat input, heat output, but that is not my objective. My objective is simply to provocate you that wherever you are in the plant, where high temperature appliances are there, you must make an attempt to do the heat balance and do not stop just by doing heat balance, but think beyond. Analyze each heat output step and see what can be done. Here the concept of capture, concept of reuse, and the third concept which we have not explored over here is the concept of switch, that is from fuel oil can you switch over to another type of fuel or a mixture of fuel. So, these are the three concepts along which you must analyze your heat balance, and that is what the objective of this lecture. Now, with this I hope that some of you must be having or must be encouraged to do this exercise, so that my lectures will be useful.